Close your eyes and drift with me through the vast darkness of space, back to a time before our world existed, before the earth beneath your feet, before the sun warming your face. There was only a cloud, a massive, slowly spinning cloud of gas and dust, floating silently in the void. This was our solar nebula, and it stretched across billions upon billions of miles of empty space, cold and patient, waiting for its moment to transform. About 4.5 billion years ago, something stirred this ancient cloud. Perhaps a nearby star exploded in a brilliant supernova, sending ripples through space like a stone dropped in a cosmic pond. Whatever the trigger, our nebula began to collapse, pulled inward by its own gravity, spiraling ever faster, growing denser at its heart. And there, in that swirling center, something remarkable was being born. As the cloud spun, it flattened into a disk. Imagine a dancer's skirt, spinning and spreading wide. At the very center, where the pressure grew immense and temperatures soared to millions of degrees, hydrogen atoms began to fuse together. In that moment of ignition, our sun burst into life. It contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets, even the dust between worlds, makes up less than 0.2%. The sun is not just the center of our solar system. It is, quite literally, almost everything. But let's drift outward now, away from that blazing newborn star, toward the inner regions where rocky worlds would form. Here, close to the sun's heat, only materials that could withstand intense temperatures survived. Metals and silicates, the building blocks of stone. These particles collided and stuck together, slowly, patiently, growing from pebbles to boulders to mountains floating in space. Over millions of years, these planetesimals, as we call them, continued their cosmic dance of collision and growth. The first of these rocky worlds to take shape was Mercury, the smallest of the 8 planets. Nestled closest to the sun, Mercury is only slightly larger than our own moon, and yet it holds the distinction of being the swiftest world in our solar system. It races around the sun at an average speed of about 105,000 miles per hour, completing its entire orbit in just 88 Earth days. If you could stand on Mercury's scorched surface during its day, you would witness something almost magical. The sun appearing to stop in the sky, move backward, then stop again and resume its original direction. This strange dance happens because of Mercury's unusual relationship between its rotation and its orbit. Moving outward, we come to a world shrouded in mystery for most of human history. Venus, named for the Roman goddess of love and beauty, gleams brilliantly in Earth's sky, the brightest natural object after the sun and moon. But beneath those beautiful clouds lies a hell's cape beyond imagination. Venus rotates so slowly on its axis that a single day on Venus, one complete rotation, takes 243 Earth days. Even more peculiar, Venus spins in the opposite direction from most other planets, meaning the sun rises in the west and sets in the east. If you had the patience to watch, you would see that a year on Venus, one trip around the sun, actually takes less time than a single Venusian day. The planet completes its orbit in just 225 Earth days, making it the only planet where a day is longer than a year. And then, floating in what scientists call the Goldilocks zone. Not too hot, not too cold, we find our home. Earth, the third planet from the sun, occupies a narrow band of space where water can exist in all 3 states: solid ice, liquid oceans, and gaseous vapor in the clouds. This rare combination, along with our protective atmosphere and magnetic field, created the perfect conditions for something extraordinary: life. Our planet orbits the Sun at an average distance of about 93 million miles, a measurement so fundamental to astronomy that we use it as a cosmic ruler, calling it 1 astronomical unit, or AU. Just beyond Earth's orbit, we encounter the red planet, Mars, named for the Roman god of war because of its blood-red appearance in our night sky, holds a special place in human imagination. This rusty world gets its distinctive color from iron oxide, essentially rust covering its surface. But Mars wasn't always the cold, dry desert it is today. Billions of years ago, this planet likely had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface in rivers and collecting in vast lakes, perhaps even an ocean in its northern hemisphere. As you relax and let these images wash over you, picture our early solar system, the sun blazing at its heart, these 4 rocky worlds taking their places in an ancient cosmic arrangement that continues to this day, spinning through the darkness, each one unique, each one a chapter in the grand story of our celestial neighborhood. Rest now, and in a moment, we'll journey further outward, beyond the realm of rock and metal, toward the giants that wait in the outer darkness. As we drift outward from Mars, we cross an invisible boundary, leaving behind the warm inner solar system where planets are made of rock and metal. Here, in the colder reaches, we enter a realm where worlds are built from something entirely different: gas and ice, hydrogen and helium, swirling storms larger than entire planets. Welcome to the domain of the giants. Between Mars and Jupiter lies a region filled with countless rocky remnants, a band of ancient debris called the asteroid belt. These are the building blocks that never quite became a planet, prevented from coalescing by the immense gravitational influence of their enormous neighbor. Some asteroids are barely larger than a car, while others span hundreds of miles across. The largest among them, Ceres, is so substantial that astronomers now classify it as a dwarf planet. This belt serves as a kind of cosmic boundary marker, separating the small rocky worlds of the inner solar system from the gas giants beyond. And what a giant awaits us! Jupiter, the 5th planet from the Sun, is a world so massive that it defies easy comprehension. If you could somehow gather together all the other planets in our solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and place them on a cosmic scale, Jupiter would outweigh them all combined, more than twice over. This colossal world is so large that 1,300 Earths could fit inside its volume. To put it another way, Jupiter alone contains more than 2/3 of all the planetary mass in our entire solar system. Floating there in the darkness, Jupiter appears as a masterpiece of swirling bands, cream-colored zones and rust-colored belts, wrapped around the planet like ribbons on an enormous sphere. These bands are massive atmospheric jet streams, racing around the planet at hundreds of miles per hour. And there, in the southern hemisphere, you can see it, the Great Red Spot, a storm so vast that Earth could tumble through it 3 times side by side. This is not a storm that lasts for days or weeks. The Great Red Spot has been raging for at least 400 years, since astronomers first observed it through primitive telescopes in the 1600s. Some scientists believe it may be far older, perhaps thousands of years old, a storm that has outlasted entire civilizations on Earth. But Jupiter is more than just a giant storm-tossed world. It's a planet with a family, a system unto itself. Jupiter has at least 95 known moons orbiting around it, a collection of worlds that reads like a catalog of cosmic diversity. 4 of these moons are particularly special, large enough to be seen from Earth with even modest telescopes. These are the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Their names echo through mythology: Io, Europa, Ganymede, and Callisto. Let your mind wander to Europa, Jupiter's ice-covered moon. Beneath a shell of ice that could be 10 to 15 miles thick lies something extraordinary. A vast ocean of liquid water, kept warm by tidal forces from Jupiter's immense gravity, flexing and heating the moon's interior. This hidden ocean may contain more than twice the amount of water found in all of Earth's oceans combined. And where there is liquid water warmed and rich in minerals, there is the possibility, however remote, of life. Europa represents one of the most promising places in our solar system to search for life beyond Earth. Drifting further outward, at nearly twice Jupiter's distance from the Sun, we encounter the jewel of the solar system. Saturn, the sixth planet, needs no introduction to anyone who has gazed upon its image. Those magnificent rings, stretching out into space, make Saturn instantly recognizable. But here's something that seems almost impossible. Despite being the second largest planet in our solar system, with a diameter of about 74,000 miles, Saturn is so light, composed primarily of hydrogen and helium, that if you could find a bathtub large enough, Saturn would actually float in water. It's the only planet in our solar system with a density less than water itself, at just about 7/10 the density of water. Those rings, though they appear solid from a distance, are actually composed of countless individual pieces of ice and rock, ranging in size from tiny grains of sand to chunks as large as houses, all orbiting Saturn in an impossibly thin disk. The rings stretch out more than 200,000 miles from the planet, yet they're incredibly thin, in most places only about 30 feet thick. If you scaled the rings down to the thickness of a piece of paper, they would be nearly a mile wide. They're so delicate that scientists believe they may be relatively young by cosmic standards, perhaps only a few 100 million years old, possibly the remains of a moon that wandered too close and was torn apart by Saturn's gravity. And Saturn, like Jupiter, commands its own retinue of moons, at least 146 known satellites orbiting this ring giant, including Titan, the only moon in our solar system with a substantial atmosphere. Titan's atmosphere is actually thicker than Earth's, composed primarily of nitrogen, shrouding the moon's surface in an orange haze that hid its secrets until spacecraft ventured close enough to peer through the veil with radar. Beneath those clouds, Titan has weather, seasons, and even lakes and rivers, though they flow not with water, but with liquid methane and ethane, creating an alien landscape that mirrors Earth in strange and wonderful ways. Let yourself float here, in the soft light of distant Saturn, watching the shadow of the rings sweep across the planet's cloud tops. The solar system is so much larger than we've yet explored, stretching outward into deeper cold, toward ice giants and distant wanderers at the very edge of the sun's influence. But for now, rest in this moment, suspended between worlds, breathing slowly, as we prepare to journey even further into the outer darkness. As we drift further from the sun, the light grows dimmer, the warmth fades to a distant memory. Here, in these far reaches, the solar system takes on a different character, colder, quieter, more mysterious. We've traveled nearly 2 billion miles from the sun now, and ahead of us looms a world unlike any we've encountered so far. Uranus, the seventh planet from the sun, is a world that quite literally rolls through space. While most planets spin like tops, with their axes roughly perpendicular to their orbital paths, Uranus is tilted on its side at an angle of 98 degrees. Imagine a planet lying on its side as it orbits the sun, with one pole pointing almost directly at our star for half its orbit, then the other pole for the remaining half. This extreme tilt means that Uranus experiences the most unusual seasons in the solar system. Each pole gets around 42 years of continuous sunlight, followed by 42 years of complete darkness. A single year on Uranus lasts 84 Earth years, meaning if you were born during its northern hemisphere summer, you would be middle-aged by the time winter arrived. This pale blue-green world gets its distinctive color from methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. But Uranus holds deeper mysteries beneath its serene appearance. Unlike Jupiter and Saturn, which have relatively small rocky cores surrounded by massive envelopes of gas, Uranus is thought to have a different internal structure. Scientists believe its interior is dominated by a thick, slushy mantle of water, methane, and ammonia ices surrounding a rocky core. This composition has led astronomers to classify Uranus not as a gas giant, but as an ice giant, a distinct category of planet. The journey continues outward, another billion miles into the cold and the dark, to the most distant of the major planets. Neptune, the eighth planet from the Sun, orbits so far away that it takes 165 Earth years to complete a single trip around the Sun. In fact, since its discovery in 1846, Neptune has only just completed its first full orbit in 2011. If you had been alive when Neptune was discovered, neither you nor your children nor your grandchildren would have lived to see it return to the same point in its orbit. Neptune appears as a deeper, richer blue than Uranus, also due to methane in its atmosphere, though scientists are still investigating why Neptune's blue is more vivid. But don't let its serene appearance fool you. Neptune hosts the fastest winds in the entire solar system, with storms racing across its surface at speeds exceeding 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic winds tear through an atmosphere billions of miles from the sun's warming influence, driven by internal heat radiating from deep within the planet itself. Neptune has 14 known moons, but one stands out as particularly remarkable. Triton, Neptune's largest moon, is one of the coldest objects in the solar system, with surface temperatures plunging to -391 degrees Fahrenheit. Despite this incredible cold, Triton is geologically active. Voyager 2, during its flyby in 1989, discovered geysers on Triton's surface, erupting plumes of nitrogen gas and dark dust particles more than 5 miles into the thin atmosphere. Even more intriguing, Triton orbits Neptune in a retrograde direction, backward compared to Neptune's rotation, suggesting that this moon didn't form alongside Neptune but was instead captured by the planet's gravity, perhaps stolen from the Kuiper belt beyond. And now we've reached the frontier, the edge of the realm of planets. But the solar system doesn't end at Neptune. Beyond lies a vast region called the Kuiper belt, a disc-shaped zone extending from Neptune's orbit outward to about 50 astronomical units from the Sun. Here, in this frigid realm, drift countless icy bodies, remnants from the solar system's formation, preserved in the deep freeze of space like cosmic time capsules. These are the building blocks that never coalesced into planets, scattered and preserved in the cold darkness. Among the Kuiper belt objects, one captured humanity's heart for generations. Pluto, once considered the ninth planet, orbits in this distant realm at an average distance of about 3.7 billion miles from the Sun. From Pluto's surface, the Sun would appear as merely a bright star in the sky, offering little warmth. Pluto's day one rotation takes about 6.4 Earth days, and it's locked in an orbital resonance with Neptune, completing 3 orbits for every 2 that Neptune makes. This gravitational dance ensures the two worlds never collide, despite their orbital paths crossing when viewed from above. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex and beautiful than anyone had imagined. Mountains of water ice as tall as the Rockies, a vast heart-shaped plain of frozen nitrogen, and a thin blue atmosphere extending high above the surface. Pluto has 5 known moons, the largest of which, Charon, is so big relative to Pluto that the two worlds actually orbit a common point in space between them. They're more like a binary system than a planet and moon, two worlds locked in an eternal dance, always showing the same face to each other as they waltz through the outer darkness. But even Pluto is not the edge. The solar system extends far beyond, into regions we're only beginning to understand. The Kuiper belt itself stretches outward, gradually thinning and merging into the scattered disk, where objects follow wild, eccentric orbits, flung there by gravitational encounters billions of years ago. Breathe deeply and let your mind expand with the scale of it all. We've journeyed from the sun to the very frontier of the planetary realm, covering billions of miles, passing worlds of rock and metal, gas and ice, each one a unique creation in the grand architecture of our cosmic neighborhood. Rest now, floating in the quiet darkness beyond Neptune, where the sun is just a bright point of light and the stars shine with unwavering clarity. Let your consciousness drift even further now, beyond the Kuiper belt, into a realm so vast and distant that light from the sun takes hours to reach it. We're entering a region where our solar system begins to blur into interstellar space, where the sun's influence grows faint but still reaches out with invisible fingers of gravity. Far beyond Pluto, anywhere from 2,000 to 100,000 astronomical units from the sun, lies a spherical shell of icy objects called the Oort Cloud. This is the true edge of our solar system, a vast reservoir of comets surrounding our sun like a cosmic bubble. The Oort Cloud is so distant that objects at its outer edge are nearly a third of the way to the nearest star. If you could stand at the inner edge of the Oort Cloud and look back toward the sun, you would see it as merely a bright star among many, its warmth utterly unfelt across the trillion miles of space. These frozen wanderers in the Oort Cloud are the source of the long-period comets that occasionally grace our skies, those magnificent visitors that appear once every few centuries or millennia, following extremely elongated orbits that bring them from the outer darkness into the inner solar system. When gravitational perturbations from passing stars or the subtle tug of the galactic tide nudge an Oort Cloud object, it can begin a long fall toward the sun, taking millions of years to complete its journey inward. Speaking of comets, these ancient travelers are often called dirty snowballs, lumps of ice, dust, and rock that have remained largely unchanged since the solar system's formation. When a comet approaches the sun and warms, the ice doesn't melt but instead transforms directly from solid to gas in a process called sublimation. This releases dust and gas that streams away from the comet, pushed by the solar wind and radiation pressure from the sun. The result is the magnificent tail, or rather, tails, plural. Comets actually develop two distinct tails: a dust tail that follows the comet's orbital path, and an ion tail made of charged particles that always points directly away from the sun, regardless of the comet's direction of travel. Now let's turn our attention back toward the inner solar system, to something that connects all these worlds, the solar wind. The sun doesn't just radiate light and heat. It also releases a constant stream of charged particles, mostly electrons and protons, that flows outward in all directions. This solar wind travels at speeds of about 1 million miles per hour, carrying the sun's magnetic field with it, creating a vast bubble around our solar system called the heliosphere. The boundary where the solar wind finally slows down and meets the interstellar medium, the thin gas between the stars, is called the heliopause. This is the true edge of the sun's domain. NASA's Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space at a distance of about 122 astronomical units from the Sun. Voyager 2 followed in 2018, crossing at a slightly different location and confirming that the boundary is not a perfect sphere but varies depending on the direction and strength of the solar wind. Within the heliosphere, we find evidence of the sun's influence everywhere. Take Earth's magnetosphere, for example, the protective magnetic bubble that surrounds our planet. Generated by the churning of molten iron in Earth's outer core, this magnetic field extends thousands of miles into space, shielding us from the solar wind and cosmic radiation. When charged particles from the solar wind interact with Earth's magnetic field, they're guided along the field lines toward the poles, where they collide with atoms in our atmosphere, creating the shimmering curtains of light we call auroras, the northern and southern lights. These same auroral displays occur on other planets with magnetic fields, too. Jupiter's auroras, powered by its immense magnetic field, are hundreds of times more energetic than Earth's. The Sun itself is not constant but goes through cycles of activity. Approximately every 11 years, the Sun transitions from a period of relative calm to one of intense activity and back again. During the peak of the solar cycle, the Sun's surface becomes covered with dark spots called sunspots, regions where intense magnetic fields suppress the usual convection of heat from below, making them appear darker than their surroundings. These sunspots can be enormous, many times larger than Earth, and they're often the birthplaces of solar flares and coronal mass ejections, powerful eruptions that hurl billions of tons of charged particles into space. When these eruptions are directed toward Earth, they can create geomagnetic storms that light up our skies with auroras visible at much lower latitudes than usual. But they can also disrupt satellites, interfere with radio communications, and even affect power grids on the ground. In 1859, the most powerful geomagnetic storm ever recorded, the Carrington event, caused auroras visible as far south as the Caribbean and caused telegraph systems across Europe and North America to fail, with some operators reporting they could send messages even with their power sources disconnected. The induced currents were so strong. The Sun has been shining for about 4.5 billion years, and it's roughly halfway through its life. In another 5 billion years or so, the Sun will exhaust the hydrogen fuel in its core. When this happens, it will begin fusing helium and will swell into a red giant, expanding outward until it potentially engulfs Mercury, Venus, and possibly even Earth. But this is so far in the future that it's almost beyond comprehension. A span of time longer than the Earth has existed, longer than life has flourished on our world. For now, the Sun burns steadily, a stable yellow star, providing the light and warmth that makes life possible on our small blue world. Every atom in your body heavier than hydrogen was forged in the heart of a star, perhaps even in the supernova that triggered the collapse of our solar nebula billions of years ago. We are, quite literally, made of stardust, children of the cosmos, contemplating the very system that gave us birth. Let that thought wash over you like a gentle wave. Rest in the knowledge that you are part of this grand cosmic story, connected to every planet, every moon, every particle of dust drifting through the solar wind. Now let's draw our attention to the smaller members of our solar family. The asteroids, the meteoroids, the fragments and wanderers that fill the spaces between worlds. These may be small, but they hold secrets about our solar system's violent past and perhaps clues to its future. We've already visited the main asteroid belt between Mars and Jupiter, but did you know that not all asteroids stay safely in that distant realm? There's a group called the Trojan asteroids that share Jupiter's orbit, clustered at two stable points, one ahead of Jupiter and one behind it, where the gravitational forces of the Sun and Jupiter balance perfectly. These points, called Lagrange points, act like cosmic parking spaces, and Jupiter has trapped thousands of asteroids in these regions. They travel along with the giant planet, preceding and following it like a royal procession through space. Other planets have Trojans too: Neptune, Mars, and even Earth has at least one small asteroid companion sharing its orbit. Closer to home, a group of asteroids follows paths that bring them near Earth's orbit. These are the near-Earth asteroids, and astronomers track them carefully because their orbits occasionally intersect with ours. Most are small, ranging from a few feet to several miles across, but even a small asteroid impact could cause significant damage if one were to strike our planet. This isn't just theoretical concern. Earth bears the scars of past impacts. The most famous is the Chicxulub crater in Mexico, created 66 million years ago when an asteroid roughly 6 miles wide struck Earth, triggering the mass extinction event that ended the age of the dinosaurs. But not all space rocks make it to the ground intact. Every day, Earth's atmosphere protects us from countless small meteoroids, bits of dust and rock, most no larger than a grain of sand. When these tiny travelers enter Earth's atmosphere at speeds of up to 45 miles per second, friction with air molecules heats them to thousands of degrees, causing them to vaporize in brilliant streaks of light we call meteors or shooting stars. On an average night, if you're patient and watch the sky for an hour, you might see 5 to 10 meteors naturally occurring. But several times a year, Earth passes through the debris trail left behind by a comet, and we're treated to a meteor shower, with dozens or even hundreds of meteors per hour painting the sky with light. Among the most famous meteor showers is the Perseids, which occurs every August when Earth passes through the debris trail of Comet Swift-Tuttle. The particles that create these meteors are often centuries old, released by the comet during previous passes through the inner solar system, spread out along its orbital path like breadcrumbs. What's magical is that all the meteors in a particular shower appear to radiate from the same point in the sky, the constellation they're named after, because they're all traveling in parallel paths, and perspective makes them seem to originate from a single location. Now picture the largest asteroid in the main belt Ceres, which we mentioned earlier. With a diameter of about 590 miles, Ceres is massive enough that its own gravity has pulled it into a spherical shape, which is why it's classified as a dwarf planet. When NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, it discovered something unexpected: bright spots on the surface that turned out to be deposits of sodium carbonate, a type of salt, suggesting that liquid water had once existed beneath Ceres' surface and perhaps still does. Scientists believe Ceres may have a subsurface ocean, making it another intriguing location in the search for conditions that could support life. Asteroids aren't just scientifically interesting, they're also potentially valuable. Many asteroids are rich in metals like iron, nickel, platinum, and even gold. A single metal-rich asteroid just 1 mile across could contain more platinum than has ever been mined on Earth in all of human history. Some entrepreneurs and space agencies are seriously considering asteroid mining as a future industry. The resources locked in these space rocks could, in theory, support human expansion into the solar system, providing raw materials for construction and manufacturing far from Earth. Let's not forget about another category of small bodies, the dwarf planets beyond Neptune. In addition to Pluto, astronomers have identified several other large Kuiper belt objects that qualify as dwarf planets. Eris, discovered in 2005, is roughly the same size as Pluto and actually more massive. Its discovery was one of the key factors that led to the reclassification of Pluto, because if Pluto was a planet, then logically Eris should be too, and where would we draw the line? Other dwarf planets include Makemake and Haumea, each with their own peculiar characteristics. Haumea, in particular, is fascinating. It's shaped like an elongated ellipsoid, almost like a cosmic football, because it rotates so rapidly that centrifugal force has stretched it out. A day on Haumea lasts less than 4 hours, making it one of the fastest rotating large objects in the solar system. These small worlds, these fragments and wanderers, remind us that the solar system is not just about the major planets. It's a rich tapestry of objects, from the smallest grain of dust to dwarf planets thousands of miles across. Each one a piece of the puzzle, each one carrying information about how our cosmic neighborhood formed and evolved over billions of years. Breathe slowly and imagine yourself drifting among these ancient remnants, surrounded by the quiet beauty of space, where rocks that are older than Earth itself tumble silently through the void, witnesses to the entire history of our solar system. Let us turn our gaze now to the moons, those companion worlds that orbit the planets, each one a unique creation, many of them more geologically interesting than some planets. Our solar system contains over 200 known moons, and they come in an astonishing variety of forms. Consider Io, one of Jupiter's Galilean moons. This world is the most volcanically active body in the entire solar system. While you rest here, listening to these words, Io's surface is being constantly reshaped by hundreds of active volcanoes, some of which spew sulfur and sulfur dioxide hundreds of miles into space. The cause of this incredible volcanic fury is tidal heating, Jupiter's immense gravity, along with the gravitational tugs from Io's neighboring moons Europa and Ganymede, continuously flex and squeeze Io's interior, generating tremendous heat through friction. The surface of Io is painted in brilliant yellows, oranges, reds, and blacks, the colors of sulfur and sulfur compounds, making it look unlike any other world we know. Journey with me now to Enceladus, a small icy moon of Saturn, barely 300 miles in diameter. You might expect such a small, distant world to be frozen and dead, but Enceladus holds a spectacular secret. In 2005, the Cassini spacecraft discovered enormous geysers erupting from cracks near Enceladus's south pole, shooting plumes of water ice and vapor 62 miles into space. These geysers are fed by a global ocean of liquid water beneath the moon's icy shell, kept warm by tidal heating from Saturn. What makes this even more remarkable is that Cassini detected organic molecules, the building blocks of life, in the geyser plumes, making Enceladus another prime candidate in the search for extraterrestrial life. Speaking of Saturn's moons, let's revisit Titan for a moment, because this world deserves more of our attention. Titan is larger than the planet Mercury, and it's the only moon in the solar system with a dense atmosphere. In fact, its atmospheric pressure at the surface is about 50% greater than Earth's at sea level. This thick atmosphere is mostly nitrogen, just like Earth's, but with a significant amount of methane. On Titan, methane plays the role that water plays on Earth. It evaporates from lakes, forms clouds, and falls as rain. Titan has a complete methane cycle with weather systems, seasonal changes, and even what appear to be dry lake beds that fill during certain seasons. Now drift to Miranda, one of Uranus's moons, and one of the strangest-looking objects in the solar system. Miranda's surface is a chaotic patchwork of different terrains. Smooth plains next to jagged cliffs and ridged regions, as if someone took several different moons and stitched them together. One cliff face, called Verona Rupes, drops approximately 12 miles down, making it the tallest known cliff in the solar system. If you could somehow fall from the top of this cliff in Miranda's weak gravity, it would take about 12 minutes to reach the bottom. Scientists believe Miranda may have been shattered by an impact in its distant past and then reassembled by gravity, its pieces coming back together in a jumbled configuration. Let's talk about Earth's moon, our constant companion, the brightest object in our night sky. The moon is unusually large relative to its parent planet. In fact, the Earth-Moon system is sometimes considered more of a double planet than a planet and satellite. The prevailing theory of the moon's formation suggests that about 4.5 billion years ago, shortly after Earth formed, a Mars-sized body called Theia collided with the young Earth. The impact was so violent that it vaporized part of both worlds, sending debris into orbit around Earth. This debris eventually coalesced to form the moon. This theory explains why the moon's composition is similar to Earth's mantle but lacks a large iron core. The moon formed from the outer layers of both bodies, while Earth retained most of the dense metallic material. The moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. This happens because tidal interactions between Earth and moon transfer rotational energy from Earth to the moon's orbit. Billions of years ago, the moon was much closer, and Earth's day was much shorter, perhaps only 5 or 6 hours long. As the moon has moved away, it has slowed Earth's rotation, lengthening our days. In the distant future, both Earth and moon will become tidally locked to each other, just as the moon already shows only one face to Earth, always keeping the same hemisphere pointed toward us. Saturn's rings deserve another moment of wonder. While Saturn's ring system is the most spectacular, it's not alone. Jupiter, Uranus, and Neptune all have ring systems too, though much fainter and harder to detect. Jupiter's rings are thin and composed mainly of dust kicked up by micrometeorite impacts on its small inner moons. Uranus has 13 known rings, dark and narrow compared to Saturn's bright, broad bands. Neptune's rings are unusual because they're not uniform. They have brighter arcs where material has clumped together, possibly due to the gravitational influence of Neptune's moon Galatea. There's a fascinating mathematical concept related to rings called the Roche limit, the distance within which a large body's tidal forces would tear apart a smaller body held together only by its own gravity. Saturn's magnificent rings exist within Saturn's Roche limit, which is why the material forms a ring system rather than coalescing into a moon. Any moon that ventured too close would be pulled apart by tidal forces, its material spreading into a ring. This same principle explains why you'll never find large moons orbiting very close to their parent planets. Consider Phobos, the larger of Mars's two tiny moons. Phobos orbits Mars at a distance of only about 3,700 miles above the surface, so close that it orbits Mars 3 times every Martian day. This means that if you were standing on Mars, you would see Phobos rise in the west and set in the east, opposite to the motion of Earth's moon. But Phobos won't be around forever. It's gradually spiraling inward, moving about 6 feet closer to Mars every 100 years. In about 50 million years, Phobos will either crash into Mars or, more likely, be torn apart by tidal forces when it crosses Mars's Roche limit, potentially giving Mars a ring system of its own. Finally, let's appreciate Ganymede, the largest moon in the solar system. Ganymede is bigger than the planet Mercury, with a diameter of 3,273 miles. If it orbited the Sun directly instead of Jupiter, it would certainly be classified as a planet. Ganymede is the only moon known to have its own magnetic field, generated by convection in its liquid iron core. This magnetic field creates a miniature magnetosphere, a protective bubble within Jupiter's much larger magnetosphere. Beneath Ganymede's icy surface, scientists believe there may be a saltwater ocean sandwiched between layers of ice, potentially containing more water than all of Earth's oceans combined. Let these worlds of ice and rock and metal drift through your mind. Each moon is a world unto itself, with its own story, its own geology, its own mysteries waiting to be explored. Some harbor hidden oceans, others erupt with volcanoes, and still others bear the scars of ancient violence. Reminders that the solar system has always been a dynamic, ever-changing place. Close your eyes and float peacefully among these moons, bathed in the soft light reflected from their parent planets, surrounded by the gentle silence of space. Our solar system is not a static clockwork, frozen in time. It is a living, breathing system, constantly changing, evolving, full of motion and transformation. Let's explore some of the dynamic processes that shape our cosmic home. Every planet in our solar system rotates on its axis, but they don't all spin at the same speed. Jupiter, despite being the largest planet, has the shortest day of any planet in the solar system. This massive world completes one full rotation in just under 10 hours, 9 hours and 56 minutes to be precise. This rapid rotation causes Jupiter to bulge noticeably at its equator. The planet's equatorial diameter is about 6,824 miles greater than its polar diameter, making Jupiter visibly oblate, flattened at the poles and bulging at the middle, like a ball of dough spinning on a potter's wheel. The Sun itself rotates, but not as a solid body, because it's made of plasma rather than solid rock. Different parts of the Sun rotate at different rates. At the Sun's equator, one rotation takes about 25 days, but near the poles, a rotation takes about 35 days. This differential rotation plays a crucial role in generating the Sun's magnetic field and contributes to the 11-year solar cycle we discussed earlier. The Sun's magnetic field lines get twisted and tangled by this uneven rotation, eventually becoming so stressed that they snap and reconnect, releasing tremendous energy in solar flares. Now picture Venus again, that beautiful but deadly world. We mentioned earlier that Venus rotates backward and very slowly, But there's more to this story. Venus's thick atmosphere actually rotates much faster than the planet itself. Winds in Venus's upper atmosphere race around the planet at speeds up to 225 miles per hour, circling the entire planet in just 4 Earth days, while the solid surface below takes 243 days to complete one rotation. This phenomenon is called superrotation, and scientists are still working to fully understand what drives these incredibly fast winds on such a slowly rotating planet. Let's return to Earth and consider something we often take for granted: our seasons. Earth's axis is tilted at an angle of 23.5 degrees relative to its orbital plane. This tilt is what gives us seasons. When the northern hemisphere is tilted toward the sun, it experiences summer while the southern hemisphere has winter, and vice versa. But Earth's tilt isn't constant over very long time scales. It slowly wobbles like a spinning top, a motion called axial precession, which takes about 26,000 years to complete one full cycle. Right now, Earth's axis points toward Polaris, the North Star, but in 13,000 years, it will point in a different direction, and the star Vega will become our northern pole star. Mars experiences seasons too, and they're even more pronounced than Earth's because Mars has a more elliptical orbit and a similar axial tilt of about 25 degrees. But Mars also undergoes dramatic seasonal changes that dwarf anything we experience on Earth. During Martian winter, about 25% of the planet's entire atmosphere freezes out at the poles, forming vast caps of carbon dioxide ice, dry ice. In summer, this carbon dioxide sublimates back into gas, returning to the atmosphere. This seasonal exchange of atmospheric mass is so significant that it causes measurable changes in Mars's atmospheric pressure throughout its year. The asteroid belt, despite its name, is actually mostly empty space. If you were flying a spacecraft through the asteroid belt, your chances of randomly hitting an asteroid would be incredibly small. The total mass of all the asteroids in the main belt combined is less than 5% of the Moon's mass. Hollywood movies often depict the asteroid belt as a dense field of tumbling rocks requiring skillful navigation, but in reality, asteroids are typically millions of miles apart. Spacecraft regularly pass through the belt without any special maneuvering or concern about collisions. Here's something that connects the inner and outer solar system in an unexpected way. Jupiter acts as a gravitational shield for Earth. Jupiter's immense mass and its position in the outer solar system means that its gravity deflects or captures many comets and asteroids that would otherwise make their way into the inner solar system. Computer simulations suggest that without Jupiter, Earth would experience far more impacts from comets and large asteroids, perhaps hundreds of times more frequently. In this sense, we owe our relatively peaceful existence, at least in part, to our giant neighbor. Jupiter's gravity has shaped the architecture of the entire solar system. The planets don't orbit in perfect circles, but in ellipses, oval-shaped paths. Mercury has the most eccentric orbit of all the planets, meaning its distance from the Sun varies considerably. At its closest approach, called perihelion, Mercury is about 29 million miles from the Sun. At its farthest point, aphelion, it's about 43 million miles away. This variation affects how much heat Mercury receives. It gets more than twice as much solar energy at perihelion compared to aphelion, creating extreme temperature variations even beyond those caused by its slow rotation. Earth's orbit is also elliptical, though much less so than Mercury's. Interestingly, Earth is actually closest to the Sun during Northern Hemisphere winter, around early January, and farthest in early July during Northern Hemisphere summer. Earth is about 3 million miles closer to the Sun in January than in July. This seems counterintuitive until you remember that Earth's seasons are caused by axial tilt, not distance from the Sun. The angle at which sunlight strikes the Earth matters far more than the relatively small variation in distance. Speaking of orbital mechanics, there's a beautiful mathematical relationship called orbital resonance that occurs when two orbiting bodies exert regular, periodic gravitational influence on each other. We mentioned earlier that Pluto and Neptune are in a 3-to-2 orbital resonance. For every 3 orbits Pluto completes, Neptune completes exactly 2. Jupiter's moons provide another elegant example. 3 of the Galilean moons, Io, Europa, and Ganymede, are locked in a 1-to-2-to-4 resonance. For every 1 orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This synchronization is not coincidental. It's the result of gravitational interactions over millions of years, pulling the moons into this stable configuration. Finally, consider the sheer distances involved in space travel within our solar system. Light, traveling at 186,000 miles per second, takes about 8 minutes to travel from the Sun to Earth. But that same light takes over 5 hours to reach Pluto at its average distance. When NASA's New Horizons spacecraft flew past Pluto, the radio signals carrying its data and images back to Earth took 4.5 hours to arrive, traveling at the speed of light. The spacecraft itself took 9.5 years to make the journey, even though it was traveling at about 36,000 miles per hour relative to Earth, one of the fastest spacecraft ever launched. Rest now in the vastness of space, feeling the gentle rhythms of orbital motion, the patient turning of worlds, the slow dance of gravity that has continued for billions of years and will continue for billions more. Everything moves, everything turns, everything follows the invisible threads of gravity that connect all things in our solar family. As we drift deeper into our journey through the solar system, let's explore some of the mysteries that still puzzle scientists and the remarkable discoveries that have transformed our understanding of our cosmic neighborhood in recent years. Deep beneath the surface of Europa, that ice-covered moon of Jupiter we spoke of earlier, scientists believe the ocean may be over 60 miles deep, more than 10 times deeper than the deepest part of Earth's oceans. The pressure at the bottom of Europa's ocean would be immense, yet hydrothermal vents similar to those on Earth's ocean floor might exist there, heated by tidal friction. On Earth, such vents support entire ecosystems independent of sunlight, with strange creatures thriving in the hot, mineral-rich water. Could similar life exist in Europa's dark ocean? It's one of the most tantalizing questions in planetary science. Let's turn our attention to a puzzle that has intrigued astronomers for decades: the mystery of Planet 9. Mathematical models of the outer solar system suggest there might be an undiscovered planet lurking in the distant darkness, far beyond Neptune. Several extremely distant objects in the Kuiper Belt have strangely aligned orbits, all tilted in the same direction and clustered together in a way that seems unlikely to be coincidental. Some scientists propose that a planet roughly 5 to 10 times Earth's mass, orbiting hundreds of times farther from the Sun than Earth does, could be gravitationally shepherding these objects into their unusual orbits. If Planet 9 exists, it would take 10 to 20,000 years to orbit the Sun, and it remains hidden because of its incredible distance and the faint light it reflects. Now consider the Sun's corona, its outer atmosphere that extends millions of miles into space. During a total solar eclipse, when the moon blocks the Sun's bright disk, the corona becomes visible as a beautiful, pearly halo. But here's the mystery: the corona is much hotter than the Sun's surface. The Sun's surface, called the photosphere, has a temperature of about 10,000 degrees Fahrenheit. Yet the corona, which is further from the Sun's core where the energy originates, reaches temperatures of several million degrees Fahrenheit. This seems to violate basic physics, like finding that the air gets hotter as you move away from a campfire. Scientists call this the coronal heating problem, and while several theories exist involving magnetic fields and plasma waves, we still don't fully understand how the corona gets so hot. Venus presents us with another atmospheric mystery. The entire planet is shrouded in clouds made of sulfuric acid, and these clouds completely obscure the surface from visible light. But recent observations have detected something unexpected in Venus's atmosphere: phosphine gas. On Earth, phosphine is primarily produced by biological processes, microbes that thrive in oxygen-free environments. The discovery of phosphine in Venus's clouds sparked excitement and debate. Could there be microbial life floating in Venus's clouds, high above the hellish surface, where temperatures are more moderate? Or is there some unknown chemical process producing the phosphine? The question remains open, inviting us to reconsider what we thought we knew about this hostile world. Here's a remarkable fact about water in our solar system. Earth isn't even close to being the most water-rich world. When scientists tally up all the water in the solar system, Earth contains only a tiny fraction of it. Europa alone may have more than twice Earth's water. Add in Ganymede, Callisto, Enceladus, Titan, and several other icy moons, and the outer solar system contains vastly more water than the inner planets. Water, it turns out, is relatively common in the solar system. It's liquid water at the right temperature that's rare. Now drift with me to Saturn's hexagon, one of the strangest features in the entire solar system. At Saturn's north pole, there's a massive, persistent cloud pattern in the shape of a nearly perfect hexagon. Each side of this hexagon is wider than Earth's diameter, and the structure has been observed for decades, rotating with the planet. The hexagon is a standing wave pattern in Saturn's jet stream, created by the interaction of different wind speeds, but nothing quite like it exists anywhere else. It's a reminder that nature can create geometric forms that seem almost impossibly orderly. Mercury, our smallest planet, holds a surprise beneath its cratered surface. Despite being so close to the sun, with daytime temperatures soaring to 800 degrees Fahrenheit, Mercury has water ice at its poles. This seems impossible until you consider Mercury's axial tilt. Mercury's axis is nearly perpendicular to its orbit, meaning its poles never receive direct sunlight. Deep craters at the poles remain in permanent shadow, perpetual darkness where temperatures plunge low enough for water ice to survive, protected from the sun by crater walls that never see daylight. Radar observations have confirmed deposits of ice, possibly mixed with organic compounds, preserved in these frozen shadows. Let's contemplate the magnetospheres of the outer planets. Jupiter's magnetosphere is enormous. If we could see it from Earth, it would appear larger than the full moon in our sky, despite being over 1,000 times farther away. This magnetic bubble extends over 3 million miles in the direction of the Sun and trails out behind Jupiter in a magnetotail that stretches beyond Saturn's orbit, a distance of over 400 million miles. Jupiter's rapid rotation and its metallic hydrogen interior create this immense magnetic field, which is about 20,000 times stronger than Earth's. Within this magnetosphere, trapped particles create radiation belts so intense that they would be lethal to humans and can damage spacecraft electronics. Here's something that connects past and future. Several spacecraft have left or will leave our solar system, carrying messages from humanity to any civilization that might someday find them. Voyager 1 and Voyager 2 each carry a golden record, a phonograph record with sounds and images from Earth, greetings in multiple languages, music from different cultures, and diagrams showing Earth's location in the galaxy. These craft are now in interstellar space, traveling outward at about 35,000 miles per hour. In about 40,000 years, Voyager 1 will pass within about 1.5 light-years of a star called Gliese 445. By then, human civilization may be unrecognizably different, or perhaps vanished entirely, but these craft will continue their silent voyage, ambassadors from a moment in time when humanity first reached beyond its home world. Consider the geological diversity among the terrestrial planets. Venus has over 1,600 major volcanoes and probably many more smaller ones, though it's unclear how many are currently active. Venus appears to have been resurfaced by massive volcanic activity about 300 to 600 million years ago, covering over much of the older terrain. Mars, meanwhile, is home to Olympus Mons, the largest volcano in the solar system. A shield volcano so massive it covers an area roughly the size of Arizona and stands about 16 miles high, nearly 3 times the height of Mount Everest. The volcano is so wide that if you stood on the summit, you couldn't see the base. It would be beyond the horizon in all directions. Let yourself sink into the wonder of these mysteries and marvels. Our solar system is filled with puzzles waiting to be solved, questions that beckon us to explore further, to look more closely, to never stop asking why and how. Each answer we find opens new questions, drawing us deeper into understanding the magnificent complexity of our cosmic home. As you rest peacefully, imagine the grand ballet of celestial motion that surrounds us. Every object in the solar system is moving, not just orbiting, but traveling through space together as part of a much larger cosmic dance. Our entire solar system is in motion through the galaxy. The Sun, along with all its planets, moons, asteroids, and comets, orbits the center of the Milky Way galaxy at a speed of about 514,000 miles per hour. Even at this incredible velocity, it takes our solar system approximately 230 million years to complete one orbit around the galactic center. The last time Earth was in this position in the galaxy, dinosaurs were just beginning to appear on our world. We call this immense time span a galactic year, or sometimes a cosmic year. Now picture the ecliptic, the plane in which Earth orbits the Sun. Most of the planets orbit roughly in this same plane, within a few degrees of the ecliptic. This is not coincidental. It's evidence of the solar system's origin from a flattened disk of material. But not everything follows this rule. Pluto's orbit is tilted about 17 degrees from the ecliptic, which is one reason it sometimes crosses inside Neptune's orbit. During a 20-year period of Pluto's 248-year orbit, it's actually closer to the Sun than Neptune is, though the orbital resonance we mentioned earlier ensures they never collide. Let's talk about something called libration, a subtle wobble in the Moon's motion that allows us to see slightly more than half of its surface over time. Although the Moon is tidally locked to Earth, always showing us the same face, libration allows us to peek around the edges. Over the course of many observations, we can actually see about 59% of the Moon's surface from Earth, even though at any given moment we see only 50%. This wobbling motion happens because the Moon's orbit is elliptical, causing its orbital speed to vary slightly, while its rotation rate remains constant. Deep in the Sun's core, nuclear fusion converts hydrogen into helium, and in the process, about 4 million tons of matter is converted into pure energy every single second according to Einstein's famous equation, E equals mc squared. This is the power source that has sustained life on Earth for billions of years, and it will continue for billions more. Every ray of sunlight that warms your face, every photon that enables a plant to grow, began its journey in the unimaginable heat and pressure of the Sun's core, where temperatures reach about 27 million degrees Fahrenheit. But here's something remarkable about those photons. While they travel from the Sun to Earth in just 8 minutes, the journey from the Sun's core to its surface takes much longer. Photons don't travel in straight lines through the Sun. Instead, they're constantly absorbed and re-emitted by atoms in the Sun's dense interior, following a random zigzag path. This random walk means a photon generated in the core might take anywhere from 10,000 to 170,000 years to reach the Sun's surface, bouncing around in the darkness before finally escaping into space. Consider the barycenter, the center of mass around which two bodies orbit each other. Most people think of the Moon orbiting Earth, but technically, both Earth and Moon orbit their common barycenter. Because Earth is so much more massive, this point lies inside Earth, about 1,000 miles beneath the surface, roughly 3/4 of the way from Earth's center to its surface. So Earth actually wobbles slightly as it and the Moon orbit this point together. The same principle applies to the Sun and Jupiter. Their barycenter lies just outside the Sun's surface, meaning the Sun itself makes small orbital motions in response to Jupiter's gravity. Now drift back to the asteroid belt and consider a special group called the Kirkwood Gaps, regions in the belt where very few asteroids are found. These gaps occur at orbital distances that correspond to simple fraction orbital resonances with Jupiter. For example, at a distance where an asteroid would orbit the Sun 3 times for every one Jupiter orbit, you find very few asteroids. Jupiter's repeated gravitational tugs at the same point in these asteroids' orbits gradually push them into different orbits, clearing out these regions over millions of years. The gaps are named after Daniel Kirkwood, who discovered them in 1866. Let's revisit Mars and its thin atmosphere, which is less than 1% the density of Earth's atmosphere. This thin atmosphere cannot retain much heat, so while temperatures at Mars's equator can reach a relatively comfortable 70 degrees Fahrenheit during the day, they plunge to minus 100 degrees Fahrenheit at night. This extreme temperature swing of 170 degrees happens daily on Mars, a harsh reality that any future human colonists will need to contend with. The thin atmosphere also provides little protection from radiation, another challenge for potential Mars explorers. Here's a beautiful phenomenon you might not know about: mutual eclipses between moons. In systems with multiple large moons, like Jupiter's Galilean satellites, the moons regularly pass in front of one another as seen from Earth, or cast shadows on one another. From the surface of Io, for instance, you could watch Europa pass in front of the Sun, creating an eclipse. These moon-moon eclipses happen frequently in the Jupiter system because the moons orbit in nearly the same plane. Imagine standing on one moon and watching another moon, comparable in size to Earth's moon, slowly drift across the face of Jupiter. A sight no human has witnessed yet, but one that future space explorers might someday see. The concept of orbital energy is crucial to understanding how spacecraft navigate the solar system. When a spacecraft travels to an outer planet, it needs to gain energy, which it can do through gravity assists, flying close to a planet and using its gravity to increase speed and change direction, essentially stealing a tiny bit of the planet's orbital energy. Voyager 2 used gravity assists from Jupiter, Saturn, and Uranus to reach Neptune. Without these assists, the spacecraft would have needed much more fuel, or the journey would have taken decades longer. This technique has become essential for exploring the outer solar system. Finally, consider that every atom of oxygen you breathe was once forged in the heart of a dying star. The heavier elements, everything except hydrogen, helium, and a bit of lithium, were created either in the cores of massive stars or during supernova explosions. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it came from ancient stars that lived and died before our sun was born. The explosion of one such star may have triggered the collapse of our solar nebula, meaning our very existence might be tied to some long-dead star's violent end. We are not just in the universe. We are of the universe, made from it, connected to everything through bonds that span space and time. Rest now, feeling the motion of Earth beneath you, carrying you on its journey around the sun, while the sun carries you on its journey around the galaxy, and the galaxy itself moves through the cosmos. Everything is in motion, everything is connected, and you are part of this magnificent, eternal dance. As we approach the end of our journey through the solar system, let's reflect on what makes our corner of the universe so special, and contemplate the future that awaits these worlds we've explored together. Earth possesses something truly unique in our solar system: a large moon relative to its size. The ratio of the moon's mass to Earth's mass is larger than that of any other planet-moon system, except for Pluto and Charon, which are sometimes considered a binary system rather than a planet and moon. This unusually large moon has profoundly affected Earth's evolution. The moon stabilizes Earth's axial tilt, preventing it from varying wildly over time. Without this stability, Earth's climate would swing dramatically, potentially making it much more difficult for complex life to evolve. The moon has been a silent guardian, keeping Earth's environment relatively stable for billions of years. Let's talk about the colors of the solar system. Each planet has its distinctive hue, telling us about its composition and atmosphere. Mars is red from iron oxide, Earth is blue from its water-covered surface and nitrogen-oxygen atmosphere, Jupiter and Saturn show cream and brown bands from different chemical compounds in their atmospheres, Uranus and Neptune glow blue-green from methane, and Venus shines brilliant white from its reflective sulfuric acid clouds. If you could see all the planets lined up together, you'd witness a rainbow of worlds, each color a clue to that world's nature and history. Here's something that might surprise you. The sun loses mass over time, not just from converting matter to energy, but also from the solar wind. The sun loses about 1.5 billion kilograms of mass every second through the solar wind alone. This might sound like a lot, but the sun is so massive, about 330,000 times Earth's mass, that it would take trillions of years for this mass loss to significantly affect it. Still, over the sun's lifetime, it will lose a tiny fraction of its mass through this constant outflow of particles. Consider the zone of habitability, sometimes called the Goldilocks zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. In our solar system, this zone roughly extends from about 0.9 to 1.5 astronomical units from the Sun, encompassing Earth and, at certain times in Mars's history, Mars as well. But habitability might not be limited to this zone. The discovery of subsurface oceans on moons like Europa and Enceladus has expanded our thinking. Habitability might exist anywhere there's liquid water, heat, and the right chemistry, even on moons orbiting giant planets far from the Sun. Now picture the asteroid Bennu, a small near-Earth asteroid only about 1,600 feet across. NASA's OSIRIS-RX mission visited Bennu, collected samples from its surface, and returned them to Earth in 2023. These samples are precious because they're pristine material from the early solar system, largely unchanged for 4.5 billion years. By studying them, scientists can learn about the conditions that existed when the planets were forming, and about the organic molecules that may have seeded Earth with the ingredients for life. Bennu is like a time capsule, preserving the chemistry of our solar system's birth. Let's contemplate the fate of our solar system. We mentioned earlier that the Sun will eventually become a red giant, but the story doesn't end there. After the red giant phase, the Sun will shed its outer layers in a series of pulses, creating a beautiful planetary nebula. A glowing shell of gas expanding into space, illuminated by the hot core left behind. This core will become a white dwarf, a dense remnant about the size of Earth, but containing about half the Sun's current mass. Over trillions of years, this white dwarf will slowly cool and fade, eventually becoming a black dwarf, a cold, dark cinder, the final resting state of stars like our Sun. Here's a fascinating detail about solar eclipses. They're possible only because of an incredible cosmic coincidence. The Sun is about 400 times wider than the Moon, but it's also about 400 times farther away from Earth. This means they appear almost exactly the same size in our sky, allowing the Moon to perfectly cover the Sun's disk during a total solar eclipse. This perfect alignment is temporary on cosmic timescales. Remember, the Moon is slowly moving away from Earth. In about 600 million years, the Moon will be too far away to completely cover the Sun, and total solar eclipses will no longer be possible from Earth's surface. Consider the diversity of atmospheric phenomena across the solar system. We have dust devils on Mars that can tower miles high, lightning in the atmospheres of Jupiter and Saturn, methane rain on Titan, and auroras not just on Earth but also on Jupiter, Saturn, Uranus, and even on some moons. Each world with an atmosphere exhibits its own unique weather patterns and phenomena, shaped by that world's distance from the Sun, its rotation rate, its magnetic field, and its atmospheric composition. The solar system is a laboratory of atmospheric science, showing us countless variations on the theme of gases in motion. The concept of planetary protection is crucial as we explore the solar system. Scientists take great care to avoid contaminating other worlds with Earth life, and to avoid bringing potentially hazardous extraterrestrial material back to Earth. Spacecraft that visit potentially habitable worlds like Mars or Europa are carefully sterilized to eliminate any microbes that might hitchhike along. This isn't just about following rules, it's about preserving the scientific integrity of these worlds, ensuring that if we find life elsewhere, we can be certain it's truly alien and not something we accidentally brought from Earth. Let's end with a thought about exploration. Humans have sent robotic explorers to every planet in our solar system. Some, like Mars, we've studied extensively with multiple rovers and landers. Others, like Uranus and Neptune, we visited only briefly with a single flyby. We've landed on asteroids, orbited comets, touched the Sun's corona with the Parker Solar Probe, and sent craft beyond the heliopause into interstellar space. Each mission reveals new wonders, answers old questions, and poses new mysteries. The exploration of our solar system is an ongoing adventure, one that will continue for as long as human curiosity endures. And finally, remember this: you live on a world that orbits a fairly ordinary star, in a solar system that is one among hundreds of billions in our galaxy, which is itself one among hundreds of billions of galaxies in the observable universe. And yet, this ordinary star and its family of worlds is your home, the stage upon which all of human history has unfolded, the only place in the vast cosmos where we know with certainty that life exists. Every person you've ever known, every story ever told, every dream ever dreamed, all of it happened here, on this small world orbiting a middle-aged star in a quiet suburb of the Milky Way galaxy. You are a child of the cosmos, made of atoms forged in stars, living on a planet that has cradled life for billions of years, looking out at a universe of infinite mystery and beauty. The solar system is your birthright, your heritage, your home. And now, as you drift towards sleep, you carry with you 100 facts about this magnificent cosmic neighborhood. These worlds of ice and fire, rock and gas, light and shadow that share the sun's warmth with our precious Earth. Rest peacefully now, floating among the planets, bathed in starlight, connected to everything, part of the eternal dance of matter and energy that is our universe. Sleep well, cosmic traveler, and dream of worlds beyond imagining, waiting patiently in the darkness, holding their secrets until we are ready to discover them. But wait, before you drift completely into sleep, let me share just a few more marvels, the final pieces of our cosmic puzzle, 10 more secrets of the solar system to carry with you into your dreams. Did you know that Venus has no moons at all? Neither does Mercury. In fact, of all the planets in our solar system, only 2, Mercury and Venus, orbit the Sun without any natural satellites. Scientists aren't entirely sure why, though theories suggest that any moons they might have had in the past could have been lost due to their proximity to the Sun, or perhaps they never formed moons in the first place due to the conditions in the inner solar system during planetary formation. Now consider the beautiful rings of Saturn again, but this time think about what they're made of. The particles in Saturn's rings range from tiny grains the size of sugar crystals to house-sized chunks of ice. But here's what makes them sparkle so brilliantly. They're mostly water ice, some of the purest ice in the solar system, which is why they reflect sunlight so beautifully. Some particles also contain traces of rocky material, giving certain rings a slightly different hue. When sunlight hits these countless icy particles, each one becomes a tiny mirror, creating the magnificent display we see. Let's talk about something called the frost line, also known as the snow line in the early solar system. This was an invisible boundary in the protoplanetary disk, located roughly where the asteroid belt is now, beyond which temperatures were cold enough for volatile compounds like water, methane, and ammonia to condense into solid ice. Inside the frost line, these materials remained gaseous and were blown away by the solar wind, which is why the inner planets are rocky and relatively small. Beyond the frost line, ice could form, and these icy solids provided much more material for planet building, which is why the outer planets grew so large. This single invisible line in the ancient solar nebula determined the fundamental architecture of our solar system. Here's something extraordinary about Jupiter. It emits more heat than it receives from the Sun. In fact, Jupiter radiates about 67% more energy than it absorbs from solar radiation. This heat comes from the planet's slow gravitational contraction. Jupiter is still very gradually shrinking, and as it does, gravitational potential energy is converted to heat. This internal heat drives Jupiter's powerful weather systems and contributes to the intense activity in its atmosphere. Jupiter, in a sense, is still settling into its final form, even after 4.5 billion years. Now drift to Neptune's moon Triton once more. We mentioned earlier that Triton orbits backward, but here's another remarkable fact. Triton is doomed. Because of its retrograde orbit, tidal forces are gradually slowing Triton down and pulling it closer to Neptune. In about 3.5 billion years, Triton will cross Neptune's Roche limit and be torn apart by tidal forces, creating a spectacular ring system around Neptune that could rival or even surpass Saturn's rings. Future astronomers, if any exist, will witness Neptune surrounded by magnificent rings made from the remnants of its largest moon. Consider the South Polacan Basin on our moon, one of the largest impact craters in the entire solar system. This enormous impact basin is about 1,600 miles across and more than 8 miles deep. It's so old, dating back about 4 billion years, that many other craters have formed within it since its creation. The impact that created this basin was so powerful that it may have excavated material from the moon's mantle, providing scientists with a rare glimpse into the moon's interior composition simply by studying the rocks in this ancient scar. Here's a fact about Mars that connects to Earth's future. Mars has 2 tiny moons, Phobos and Deimos, whose names mean fear and panic in Greek, appropriate companions for the god of war. But while we've talked about Phobos's doom, Deimos has a different fate. Deimos orbits far enough from Mars that tidal forces are actually pushing it into a higher, more distant orbit, just as our moon is receding from Earth. In the far future, Deimos will drift farther and farther away, possibly eventually escaping Mars's gravity altogether to become an independent asteroid orbiting the Sun. Now think about the zodiac, those 12 constellations that the Sun appears to pass through during the year. The Sun's path through these constellations is the ecliptic we mentioned earlier, and the planets also stay close to this path as they orbit. Ancient peoples noticed that several bright objects, the planets, wandered through these constellations while the stars remained fixed. The word planet comes from the Greek planets, meaning wanderer. For thousands of years, humans have watched these wanderers move against the backdrop of stars, their motions encoding the gravitational ballet of the solar system, a cosmic clock visible to anyone who takes the time to watch the night sky over weeks and months. Let's contemplate a measurement that puts our solar system in perspective. The astronomical unit, or AU, which we defined earlier as the distance from Earth to the Sun, about 93 million miles. This unit becomes incredibly useful when discussing solar system distances. Mercury orbits at about 0.4 AU, Mars at 1.5 AU, Jupiter at 5.2 AU, and Neptune at 30 AU. The Kuiper belt extends to about 50 AU, and the Oort Cloud reaches perhaps 100,000 AU. Using this scale helps us comprehend the vast emptiness between worlds, the way distances grow as we move outward, each planet more isolated than the last. Here's our final fact, a thought to carry into your dreams. Earth is the only planet in our solar system named after a concept rather than a Roman or Greek deity. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune all bear the names of gods. But Earth, our home, comes from old Germanic words meaning simply ground or soil. While other worlds are named for gods, we named ours for the dirt beneath our feet, the soil that grows our food, the ground we walk upon. There's a humility in that, a recognition that we are bound to this world, creatures of earth and water, children of this particular place in the cosmos. Perhaps that's fitting. While we reach for the stars and dream of distant worlds, we remain, for now, people of the earth. And with that, we've completed our journey, 100 facts about our solar system, woven together into a single story of cosmic wonder. From the sun's blazing core to the frozen darkness of the Oort Cloud, from the smallest grain of dust to the mightiest giant planet, from the solar system's ancient birth to its distant future, you've traveled through space and time, accumulating knowledge like stardust. Now truly it is time to rest. Let these facts settle gently in your mind like snow falling on a quiet winter night. Let the majesty of the cosmos embrace you. You are home, here on Earth, orbiting the sun, suspended in the vastness of space, connected to everything. Sleep well, traveler. The solar system will still be here when you wake, spinning through space, ancient and patient, waiting for you to look up once more and wonder. Good night.